Conical intersection and energy funnels.
Okay, so I'll get started here. This looks to be completely different. I'll show you that there are some similarities in the Hamiltonians, at least, later. All right. Ordinarily I talk about conical intersections and how they pop up all over in chemistry. I just have flip sides here in biology. They show up in the photoprotection of DNA bases. They show up in inverted region electron transfer. In particular, this has been hypothesized in the backwards electron transfer steps in photosynthesis. They also show up, and so this is a case where they have to function sort of as slow things. And then there are cis-trans isomerization, example being the primary step in vision is a photoisomerization basically via conical intersection. And so they're a place where two potential energy surfaces actually intersect. And if you think about the crossing and our standard sort of crossing picture that we learned about in our sort of earliest days, it's the semi-classical Landau-Zener picture. And in the Landau-Zener picture, a non-adiabatic transition is allowed if fast nuclear motion makes the time derivative of an occupied orbital, if it's moving adiabatically, comparable to the energy gap divided by Planck's constant needed to reach an unfilled orbital. And you can substitute states here for orbitals if you want to be completely rigorous. And this is always true at a conical intersection where the delta E drops down to 0. But this semi-classical analysis implicitly assumes that the vibrational wave packet width is negligible. And that requires a fast wave packet for that to be true, because you've got to have high momentum components. And so we'll be talking about things where this analysis completely fails. A conical intersection has two special vibrational coordinates. Analysis goes back to von Neumann and Wigner. There's a G coordinate, which is known as the tuning coordinate, and it adjusts the energy gap to 0. And in the rate limit, this turns into dephasing, according to Redfield theory. And then there's the off-diagonal derivative coupling coordinate, and it also has to simultaneously go to 0 at a conical intersection. And in a rate limit, Redfield theory again, this turns into a rate for population transfer. So at a conical intersection, however, vibrational correlation plays a role in both population transfer and dephasing. There's no analytic theory that works in the sort of rate field way, in the sort of Redfield way. And so what the experiment I'll be telling you about, the first one, we're going to prepare and probe an electronic wave packet at a D4H Jahn-Teller distortion using polarized light. And since this is an electronic wave packet, it will have many features in common with the wave packets seen in Rydberg atoms. So you expect beating phenomena, even if there were no bath, beating phenomena if there is no coupling to the vibrations. And so the picture looks something like this. If we have a polarized field, and let us say the molecule has axis oriented this way or this way, we're always going to be exciting the electrons so that they move parallel to the field. At least their projection onto the field will be parallel. And the molecule we'll be using is this silicon naphthalocyanine. It's fairly big. If you should look at it in a sort of gross way and see porphyrin or bacterial chlorophyll, except for the extra nitrogens here and the ligands. But it's big. It rotates very slowly as a result of that. It takes half a nanosecond. The excited state lifetime is basically forever on our time scale. And so we will be able to look and see the reorientation or realignment of the electrons in the molecular plane, right here. So that realignment will be coupled to two kinds of vibrations. Rectangular deformations of the molecule, so I'm showing you the sort of planar skeleton, And then you can imagine also these diamond-type deformations where both arms squish in and the other two arms pop out. The shape of the potential surface generically looks something like this. Two wells, symmetry-related, separated by two symmetry-related saddle points. And the sort of stabilization energy, the Jan-Teller stabilization energy is called d omega. This looks just like a Marcus stabilization energy from the point of view of electron transfer. They were defined the same way, essentially independently of each other. And so which wells are deeper actually just depends on whether the detuning or the derivative coupling is stronger, and it can go either way. So the electronic wave packets that we'll make, I've just kind of illustrated the kind of thing, what would happen for a particle in a rectangular box. So imagine deforming a square box, making it slightly rectangular, and then if we were exciting in this direction, we would see, because of this lifting of the degeneracy, we would see sort of two electronic state quantum beats going back and forth, delocalized to the other well on a time scale governed by the splitting energy right here. Now, the experiments, the way we do them, we have essentially three observables. In particular, because of the polarization vectors involved, we would be completely blind to the direct transfer between a coherence and a population. Although we do have to, in talking about the theory of these, consider population transfers and coherence transfers between the two states when we work this out. But the things that we can directly measure, the way we do this experiment, we're using short pulses. The short pulses are spectrally broad enough so that you can think about them as integrating over all the vibrational coordinates of the molecule. As a result, we measure something that's pretty close to the electronic reduced density matrix, which has sort of three parts that we can measure. There's a population. This is in the magic angle signal, it's boring. There's a population difference, which measures things such as if I started on X, do I stay on X or end up on Y? And then there is a real coherence, which measures, if in one way of looking at it, if I started on XY, am I on YX or XY? Either one doesn't matter as long as I still have coherence. It turns out that this maps, if you change the basis set, to population transfer between states polarized in this way. Then the key thing that we'll use to measure this is the polarization anisotropy, which is parallel minus perpendicular over the isotropic signal parallel plus 2 perpendicular. So the magic angle is divided out, if you like. All the population dynamics is gone. And it depends on, compared to the last slide, the real coherence and the population difference when we look at the signal coming from the excited state. And there are also signals going to doubly excited states. These things have doubly excited states like the excitonic systems. And this is, these doubly excited states are there in almost all the porphyrins and whatnot. So they're going to play an interesting role in these excitonic Hamiltonians for the biexciton states that nobody's quite looked at yet, to my knowledge. So here's this signal. What you see is the magic angle signal right here. It's got the boring part, and it's just got small amplitude, high frequency vibrational quantum beats. These are Frank Condon active vibrations that everybody's been seeing for years and years. All right. Then we get to the sort of more interesting parts. There's the parallel part, a rapid drop. That's because when we probe parallel, if the electronic wave function is realigned, we're going to lose signal. Similarly, that signal grows in the perpendicular very rapidly, and the parallel and perpendicular settle down to this 4:3 ratio. And that 4:3 ratio is characteristic of delocalization in a plane. okay? And not the full delocalization that would occur if the molecule tumbled randomly through space. And so if we look at the anisotropy itself, what we're seeing is a signal that starts off at 0.4, a little bit before time 0, when our pulses are overlapping there. By time 0, it's already dropped a little bit, heading down into the vicinity of 1/10. The first 1/e time is about 80 femtoseconds. The second 1/e time is about 180. Third one's about 280. So zero order, it's 100 femtosecond type of decay, although it's definitely not exponential, right? You can see a little bit of a Gaussian type character here, and then you can see quantum beats that reproduce between a couple of versions of this. And the quantum beats go out for 3 picoseconds or so in terms of their exponential decay time. Now, these quantum beats that we see are unlike quantum beats that have been reported before in resonant pump probe experiments, these 3. The first 2 are the same thing everybody's been seeing for a long time. They're seen in parallel, perpendicular, and also in the magic angle. And so what this is telling you, since they're present in the magic angle, which measures the isotropic or population dynamics, these quantum beats are measuring, in the parallel, are measuring the modulation of the intensity of the absorption spectrum. And that occurs because the molecule manages to scoot a little bit to a place where a laser can't measure it. These very high frequency vibrations can do that. And so they show up in all 3. And that's what everybody has been seeing going all the way back to experiments by Rosker, Wise, and Tang from 85 or so. Then there are 3 vibrations here which do something unusual. They show up in the parallel, they show up in the perpendicular, but they're absent in the magic angle. So this means they have no effect on how much light is absorbed. All they cause a change in is which polarization of light the molecule absorbs. So these vibrations are modulating the direction of the electronic transition moment, flopping it back and forth from parallel to perpendicular. So these are your Jahn-Teller active vibrations.
Is the phase different in parallel and perpendicular?
It's pi different, right? And the ratio is different by a factor of 2. So perpendicular is, and so it's the phase difference that causes the anisotropy of these vibrations to be infinite within experimental error. Because when we have parallel plus 2 perpendicular on the bottom, and the phase is pi out experimentally, and the amplitudes, the denominator in the anisotropy goes to 0. And so you get these very bizarre sort of looking error distributions where it can be very large, positive or negative, but can't be a small number. Using the standard kinds of methods that people have used for a long time for Jahn-Teller active vibrations for determining the Marcus stabilization energy, we can determine the Jahn-Teller stabilization energies for these vibrations, and they're small, on the order of a millielectron volt. So almost nothing in chemical terms. And so I just want to put the Hamiltonian that we'll have to use for these into sort of form that's simple. We have, in this case, everything is dictated by symmetry. B1G symmetry, rectangular deformation vibrations will cause energy gap tuning. And so they'll split these 2 energy levels of the X and Y polarized diabatic states. The B2G symmetry vibrations will cause derivative coupling. In the diabatic basis, this looks like a simple off-diagonal term here dependent on the coordinate Q2 for the B2G symmetry vibrations. All of the totally symmetric modes, the Frank-Condon active vibrations, will belong to the seam space. And they'll do nothing to move you from one electronic state to the other. And I think that the seam space of what happens in the reaction center is probably a rather interesting question. because that's the way the experiments, I would argue, seem to be pointing. So when we linearly couple all these things, if we assume that we sort of don't have a conical intersection, that all of the vibrations that we see belong to the detuning coordinates, we get a dynamic something like this. We put the conical intersection in by allowing some to belong to derivative coupling, some to detuning. We get something like this out of our two lowest frequency vibrations. And this leaves us room for only a small amount of coupling to asymmetric solvation or missed low frequency modes. And I'll explain the theory for that in just a moment. But if we allow that, that comes from including the pulse duration effects, this recurrence can be eliminated. But the important point is that the vibrations that we see when plugged into a theory predict the fast part of the electronic dynamics with zero adjustable parameters. All right, and we don't have to do anything that we don't know to do that.
David, do you
Yes.
solve the tangent and Schrödinger equation for the coupled system?
Yes, we have.
So that's what you showed?
So the purple curve is time-dependent Schrödinger equation for the coupled system. And the blue curve is an analytic approximation to it that we can use only when we have either coupling or detuning, but not both.
Shifted harmonic oscillators.
Yes, right. And so the departure in here is where you're seeing the effects of the conical intersection, specifically, that part of the departure. So this is the part of the theory without the conical intersection, and that can be done including damping in a sort of analytic way if the curves are harmonic, using some work of Sun and Sylvie. And, oops, clicked the wrong pointer there. What you get is that the key drop in the dynamics comes from, depending on basis, either the decay of coherence or the decay of these population differences. And it depends on an exponential of -4 times a line shape function, the kind of thing that's in Mukamel's theory. What's in this line shape function is a stabilization energy, kT, which is basically filling the role of a width here, and a double integral of a correlation function. And this is high temperature semi-classical limit. But the interesting thing about this is that static vibrations will give you the fastest decay of the electronic dynamics. And this is probably connected to a kind of Zeno effect kind of thing. And so the faster the vibrations move, the slower the process gets slowed down. And this holds true also if you look at the more complicated expressions for the quantum form of this. Now, the early time dynamics driven by the coupling to the G and the H coordinates are actually independent at this level. And so what's going on with this early time dynamics? The critical thing is that there's no actual coupling right here at the conical intersection. It's the wings of the wave function that feel the coupling. And they're what's driving your system through. And you can sort of put together the decay of these things in a fairly simple form using this t-squared dependence. The critical parts are the difference in force and the variance of the vibrational wave packet along the derivative coupling coordinate and along the detuning coordinate, respectively, for causing a decay of the total measure of dephasing and thing. So this is actually tremendously different from Landau-Zener, right? Because Landau-Zener, your probability has got this sort of difference in force on the bottom and the velocity on the bottom, and then you've got a coupling on the top, and this looks just sort of tremendously different. So the conclusions from this part of the talk are that the pump probe anisotropy measures 100 femtosecond electronic reorientation. that this can be measured, that this is predicted from independently measured amplitudes of the vibrational quantum beats that we see. So, this basically means 1 milli-electron volt is driving you in about 100 femtoseconds, which is pretty fast and allows things to be quite efficient. And at low vibrational velocity, the vibrational wave packet width is what's driving the curve crossing. And that's intrinsically not in Landau-Zener and completely counterintuitive to what you would kind of expect from a Landau-Zener picture. So now I'll move to a part of this that we don't understand. This is connected to the 2D spectroscopy of this system. And so the motivation here for doing the 2D spectroscopy is that pump probe measures alignment, up, down versus left, right. But orientation distinguishes up versus down. And the pump probe really is measuring alignment. And 2D spectra measure a field, which might give you some information about this up-down thing. And the inspiration for this is really a SINA proposal a long time ago to observe the Berry phase by wave packet interferometry. Now, with 1 milli-eV kind of stabilization, we're not going to be in the adiabatic limit, but you still expect phase to play a certain role here. And so here's just the reminder of how a Berry's phase works. As you distort your way around the conical intersection, the adiabatic wave function gradually inverts its sign just through this continued evolution. And so one of the natural things then is, if we think about electronic pseudorotation, and a reference frame for thinking about that might be real rotation, right? And back in 1965 or so, Roy Gordon pointed out that rotation appears differently in microwave, which is single quantum coherence, which would look like echo coherence times, versus Raman, which is a zero quantum coherence, which would look like our pump probe anisotropy waiting time. So the question naturally is, does pseudorotation work the same way? And I can skip the 2D spectra stuff here, and I'll skip that part except to mention that we're using the combination of the echo and the anti-echo scanning over both positive and negative tau in these 2D spectra. And this is what the 2D spectra look like. They're plotted differently than in Greg Engel's talk. Excitation is here, detection is here, so that's a rotation about the diagonal. So in a sense, falling downward in energy means dropping this way. And so then the questions is, the new information in our 2D spectra basically comes from how wide this is perpendicular to the diagonal. And the question is, what's causing that? Is that a non-adiabatic electronic reorientation? Or is it coming from various totally symmetric vibrations? So the way that we do that is we use a projection slice theorem to get the echo slice through the 2D data. And the echo slice through the 2D data has a time scan in terms of, okay, it peaks, this is a finite pulse effect, and then there is a decay, and it's looking like it's around 100 femtosecond types of time scales. That's what we would expect for pseudorotation if it acts just like physical rotation. And so, because on the echo slice, T is equal to tau, so both times are decaying at once, and so that factor of 2 turns into being exactly the same time scale. So I'll skip, I think for reasons of time, exactly how we do the full diagonalization that Gerhard asked about, but we do that, and we also add some damping in, and just get to the punchline. The punchline is that when we diagonalize this fully non-adiabatic Hamiltonian and ask, does it predict what happens on the anti-diagonal, the answer is no. All right. So even though the wave function has electronically, in a sense, rotated by this 90 degrees on a certain time scale, we still have interference phenomena taking place. And so that means in particular then that Gordon's relationship between Raman-like coherence and IR-like coherence is very different for electronic reorientation than physical rotation. And excitations can still interfere after this electronic reorientation. And the echo decay that we see must be coming from the totally symmetric vibrations, must be dominated by those. So now I'll shift gears once again and tell you about a conical funnel. So a conical funnel is a 2 or more dimensional avoided crossing between potential curves. And it can be characterized in a minimal way by a static splitting and a coordinate-dependent coupling. So we have a coordinate dependence to this off-diagonal coupling, same as before. And this can be compared to a dimer Hamiltonian in a site basis, where often you have an approximately static coupling and a coordinate-dependent energy gap tuning, where the coordinate is a difference between the two normal coordinates of the two molecules. And these are the same Hamiltonian when you turn them both into the excitonic basis. So it's just a basis set transformation to connect the two. And so I'll be telling you about a free base naphthalocyanine. This is like the molecule we looked at before. We've removed the silicon, and that lifts the degeneracy between X and Y because now there are hydrogens attached along one axis and not the other. And these are the absorption and fluorescence spectra of this system. And so to compare it, as you move down to things that are more like bacteria chlorophyll, your splitting will continually increase. Or as we think about it, as decreasing as we increase the force for delocalization. So the picture is we have X and Y curves. They will intersect somewhere up here at the top of a barrier that's on the order of about 10 kcals per mole. We know from NMR in the ground state. For Frank-Condon reasons, it can't be much bigger in the excited state. And so we have to use this Hamiltonian as our sort of minimal Hamiltonian. We have a coupling that depends on the coordinates, a gap splitting which doesn't, and then what we see in the experiment is, again, a very rapid drop in parallel, a quick rise in perpendicular. We see asymmetric modes. The asymmetric modes now have finite but large anisotropies due to the lowering in symmetry. That helps us characterize the Hamiltonian more. And the other thing that we see is that as we tune around across the spectrum of the system, so the system spectrum is shown in black, and we do blue-tuned and red-tuned experiments, we see differing levels of equilibration, but the equilibration timescale doesn't change very much. It stays in the order of about 100 femtoseconds. Whether we're pumping low energy or pumping high energy, it stays about that 100 femtosecond timescale. Although when we pump at low energy, the equilibration is incomplete to the longest timescales that we've measured. So now the question is, how do we think about this? If you think about this from the point of view of the adiabatic potential curves, you're seeing that there's a pretty significant variation in the electronic character, indicated by color, over the range of coordinates that we can access, right? So Q goes to plus or minus 1 at the classical turning points of V equals 0, and these are low frequency vibrations, so we move pretty far from that sort of adiabatic point of view. From the diabatic point of view, one of the things that's going on in this system is that we have systematic resonances between V and V plus 1 for everything but the V equals 0 state on the lower curve. And neither one of these pictures is correct. the full sort of non-adiabatic basis state diagonalization, which is the black levels shown here, are actually quite dramatically different from both the adiabatic eigenstates and the diabatic basis states. And they're shifted in some sense in unpredictable ways from them, except if you look and think, okay, yeah, I've got a non-adiabatic coupling, what's it do? And so the set of conclusions for the talk is we've got something like 100 femtosecond electronic reorientation driven by 1 milli-electron volt Jahn-Teller stabilization. That the low velocity conical intersection dynamics are dominated by vibrational wave packet width and change in force, not velocity types of considerations. The non-adiabatic electronic reorientation impacts anisotropy and dephasing very differently from physical reorientation, and it's this sort of low impact on the dephasing, which is, I think, quite interesting, and I definitely don't understand this yet. And the other point is that conical funnels have non-adiabatic dynamics that is basically as fast as conical intersections, and using the same Hamiltonian as excitonic energy transfer. So I think that's relevant for other things we've heard about today. So with that, I'd like to thank the members of my group who've done this work, NSF for funding this principally, and Michael Thorwart and the organizers and the sponsors of this conference for inviting me.
Thank you, David. Questions? Great.
So in the 2D spectroscopy, as the tails of the wave function drive us through the conical intersection of this force picture, can we think of a narrowing in the inhomogeneous direction at some intermediate time? Is that a reasonable prediction, or is that wrong?
It's a complicated
And I'm thinking of
thing
the
to.
tails getting crushed in towards the middle for the opposing
Yeah, but I
force.
don't think of the tails as getting crushed in towards the middle. I think of the tails as getting moved over to the other curve and
then
swinging the center with it, so I don't avoid the uncertain. So I don't break the uncertainty principle. That might. That's a very sort of picture that comes. That's just sort of what it suggests to me.
No, that makes sense. That makes sense.
Oliver?
In your second example, or in the last example, I didn't quite get what's the role of excited state prototransfer in this model.
Okay. The role is that there isn't any.
So what you're saying is that the case before there's any transfer, or?
So yeah, so we were at first thinking that there would be a kind of a proton transfer kind of thing, or rather, to be more precise, it would be hydrogen atom transfer,
Yeah.
right? And we looked into that a bit carefully, and we at the same time deuterated the thing, and we deuterated and we saw no change. And then we started looking in carefully to what was known in the ground states from NMR studies. And the timescales were such that in NMR they could pin down that the barrier was more than 10 kcals per mole. And importantly for us, what this meant that they were able to do at NMR was that this had to occur on the NMR timescale, which means that it's slow for us. And so we have not sort of measured that time scale. And then knowing that in the ground state we had this barrier on the order of 10 kcal per mole or more, you're instantly sort of forced to imagine that if the potential surface were to change and lower that 10 kcal per mole barrier significantly, then you would cause new Frank-Condon progressions to show up in hydrogen bend type motions at the center that do not appear when you don't have hydrogens at the center, and those don't show up in the spectrum, in the linear absorption or emission spectrum. And so all of that is consistent with the barrier being essentially unchanged in the excited state, these barriers to the hydrogen atom transfer. So I naturally thought that would be what we were seeing
Yeah, but
here
I'm just
first.
asking because there are rather similar systems where this has been, or where it's said that most of the dynamics comes from hydrogen transfer, except you can.
Yeah, which systems are you in principle?
Like these corpuscles, which are very similar. It's also like it's appropriate mirror.
Uh-huh. It may be
Well,
that.
but also like you see like mode specific tunneling splitting and the original operational progression and all.
Okay. It may be
Constant
that.
acceleration of the
Is the time scale for that significantly longer than the sort of 100, 200 femtosecond time scale we're talking about here?
It might be a bit longer, but below a picosecond.
Below a picosecond. Okay.
Yeah.
In the first system you considered, you nicely compare the experimental data anisotropy to some model calculations, first shifted harmonic oscillator and then this non-adiabatic coupled one. And you get short time, very nice agreement, but not for longer times. I assume in the non-adiabatic coupled one, you essentially include two modes, is that right?
Right.
Because if
So-
I would think if you include more modes, then the thing would...
Right. So what happens is that there are three low frequency modes that we find in our experiment, right? And so we're including them in different ways in these two calculations, okay? And this part here, even with the third mode, doesn't get wiped out because of an accidental kind of degeneracy in the ratio of the frequencies. And so this peak doesn't get wiped out by that third mode, although the third mode is not shown in the calculation. It doesn't, in this particular calculation, it doesn't change it, only the lowest two frequency ones. So our conclusion is that this is probably another mode that we don't see that might be overdamped. We have some hints of a low frequency mode in our data. Again, interestingly showing up with something that looks like a maximum of about 2 wave numbers of stabilization energy coming with it. We only see that in the parallel. We don't have the signal to noise to see it in the perpendicular. It's right at the very edge. And so that could be what's causing this third one. It's just some combination of low frequency things that we have missed.
Could do just normal mode analysis and look by symmetry what modes are in charge of doing this kind of things?
So if you look at the normal mode analysis by symmetry and ask which modes are in charge, what you would be looking for are, for reasons, the very sort of lowest frequency skeletal motions of these two frequencies. And low frequency is good from the point of view of driving the dynamics faster because it's slower motion. And so what you're really looking at is basically the X getting squished to sort of a more vertical X, or doing this kind of thing, which I can't quite do, but those two types of motions are about what drive it, and they seem to line up reasonably well with some normal mode calculations on this molecule, that the frequencies are plausible.
But it doesn't explain it in the second pathway then compared to the 2D, that you say this calculations don't reproduce this 2D off-diagonal peak. So this is still completely unclear. Did I get you right?
So, well, okay. So, what happened? All right. So, for the 2D, when we did the pump probe experiment, by using very broad bandwidth pulses, in effect, we deliberately blinded ourselves to the totally symmetric Frank Condon active vibrations at low frequency. Okay? Now, we know that there are totally symmetric low frequency vibrations of this molecule. And the question would be what dominates this width right here, all right? And that's a question of the kind of correlation time for those totally symmetric low frequency vibrations. And there's not a lot of them, they're not doing a lot. The absorption spectrum of this molecule is only about 300 wave numbers wide, but evidently there's enough of them and their damping time is fast enough to cause this. So we have an explanation for that. We don't have a separate independent measurement of it. But what I find is interesting is that when we do the full non-adiabatic modeling, in contrast to the two-state modeling, right, the full non-adiabatic modeling gives a very narrow width perpendicular to the diagonal. So those kind of two-state models do not. And so this implies that that non-adiabatic modeling is allowing these interference effects to go on longer than the simple models which don't allow for interferences to cross over between the two states. That's the part that's I find remarkable and don't understand yet. Does that make sense? At least as a statement of what I don't understand. Hopefully someone can explain it.
Okay, the last question.
I was wondering about this one case where you had, I think it was anisotropy decay fastest when the nuclei were static. Was it anisotropy? Am I right in thinking that this can be basically interpreted in terms of a static disorder? Because when nuclei are not moving, you just add the energy to the...
If you have a static disorder, that will also
I mean, it's the same, isn't it the same effect? Because when
It's-
you have the nuclei static, they just add to your energy and it's different.
in the classical picture, it looks like it looks exactly like a static disorder. But this persists when you use the sort of full quantum versions of these things, or what has been advertised as the full quantum kind of line shape functions coming from Tanimura's papers, right? And whether there's some subtle error in those full quantum correlation function treatments of the line shape is one that that would take a really good theorist to find it, at least. Certainly they do a number of things correctly in terms of both the damping and the full quantum, in that they reduce in the low damping limit to some sort of quantum versions of the correlation function, and they also don't cause things to show up sort of below band edge as you're at very low temperature. So they get low temperature line shapes correct for systems with damping. And so there could be something that's wrong with it, but I think that they're also telling us something about what's intrinsic to the wave function. Not in the form I've written them down here, but it's sort of the same thing. A slower vibration does better according to that set of calculations as well. And so the way I rewrote those equations later with difference in force and variance in width is something that holds also as you drop down to a single, transform limited v equals 0 type of wave function. And so in that if you want to talk about that as if it's static inhomogeneity, I guess you could, but I wouldn't want to talk about it that way.
Is another way to look at this is this because of the symmetry of the system where the conical intersection is perfectly centered above the ground state? Is that...
That's not necessary to get this role of width in the thing, right? So,
but for the static aspect of your wave packet centered on the singularity without motion.
Well, I think the static aspect of this. Well, you want to talk about v equals 0 is static. Okay, v equals 0 harmonic oscillator wave function is static. It's really necessary only from the point of view of eliminating the effects of velocity. So I would expect that these effects of width are always there, right? And they're there even when you have some velocity. And certainly we can use the equations to show that that part of things works out, that they're there. when you're slightly off center, because the equations allow us to do that as well. So I think it's more that being dead on center isolates the effect of width rather than makes it more important.
Okay, I think we need to move on in the program.